Okay, good morning, and I would like to thank Barbara and Jan to invite me to give this talk this morning. Now I will focus on the evidence of surface rupture associated to one of the greatest intracontinental earthquake, the Assam earthquake, which is a magnitude 8.6 earthquake along the eastern Himalayas. Before I really start, I would like to acknowledge my co-authors, and particularly Aurélie and Elise, and which have been working mostly on this project, and which has now wrapped all the results and submitted the work at Science Advance just recently. I would like also to acknowledge Paul Taponnier, who was inspiring and mostly leading this work, and I would like also to say that most of the funding for this work was coming from project from the Earth Observatory of Singapore. I'd like to acknowledge also Emile, who is among us in this workshop, and also our Indian colleague at Dehradun and Jorat. Okay, so yesterday we talked about coupling along the subduction interface, mostly along the Southern American subduction zone. I would like to show this figure here, taken from Stevens and Avwak, which show similar kind of technique or of approach along the Himalayan arc, which shows this 100-kilometer wide band here in red along the whole Himalayan arc, which is quite homogeneous and shows quite a strong coupling along the whole Himalayan arc. And this is this coupling, I mean, results from the convergence between India and Tibet to the north at a rate which is around 20 millimeters per year along most of the Himalayan arc. So the 1950 earthquake is one of the great earthquakes that we know have ruptured this frontal thrust, this main frontal thrust of MFT. I will call it MFT in the rest of the talk. And it's so some is known about. What I want to say is that some is known about the earthquake history along the Himalayan arc. There are still places where there are some unknowns, and where we don't know if earthquake happened, or we don't know the timing of the earthquake. We could add here the 1714 earthquake, which was presented in a poster also by George. Some of these earthquakes occurred recently, like the 2005 earthquake with clear surface rupture. And for some earthquake, like the 1905 earthquake, still unclear if it had ruptured to the surface. And we know, I will come back to this, that for the 2015 Gorkha earthquake, clearly the rupture didn't come to the surface. And more recently, for the 1934 earthquake, it has been shown that it ruptured the surface. What I want to also to show from this figure is that from this conversion rate and this coupling along the Himalayan front, the authors here taking the moment released by the knowledge we have about the seismic activity in the last 2 or almost five centuries, show that there is a strong slip deficit due to seismic activity. So, I mean, well, there is quite a question here. Where are the earthquakes that really accommodate all the convergence here? And one of the conclusions of Stevens and Avwak was that we need some very large earthquake, magnitude 9 earthquake, that may rupture much larger part of this interface with a recurrence time of about 1,000 years. So the goal of my talk is to look more in detail what happened around the 1950 earthquake. But before that, I would just, no, this is not working, sorry. Just show you a few pictures of the 1934 surface rupture in Nepal. This is one of the stream cut here along the scarp, which is how the MFT, in fact, is visible really in the field. And in fact, what you see here is a very nice and steep topographic scarp, which is cut by several thrust faults. This is one interpretation of this river cut, and there is evidence here on this big trench that this fault here moved during the 1934 earthquake together with some other faults here in the back. And once this evidence is shown here in the river cut, this scarp here can then be followed in the field, and the rupture here is now evidence for a length of about 150 kilometers corresponding to the surface rupture of the 1934 earthquake. So we talked already about that yesterday. The 2015 earthquake occurred here mostly north and northwest of Kathmandu, with the epicenter here located near the city of Gorkha, and it propagated to the east. But as you can see, here underlined by most of the aftershocks here, the rupture remained mostly north of Kathmandu, and there is still here a 50-kilometer long stretch towards the main frontal thrust that didn't move and rupture during this earthquake. So there is evidence also that large earthquake can happen. Also large, maybe they are less large than the big magnitude 8.4 or 8.6 earthquake that may occur sometimes. And this earthquake may remain, in fact, in the back and not rupture to the surface. Okay, so we talked about yesterday again. There was already some discussion about why some of these earthquakes may just rupture part of the subduction interface, and why they could not, why they would not really rupture to the surface. Here is I take this work here by Herbert and collaborators just to show that there are also some structural reasons for some rupture to not come to the surface. And one reason for the Gorkha earthquake is probably that it remained, in fact, on the flat part here between two steeper ramps, and it didn't reach, okay, the upper part here of the ramp during the 2015 break. So there are some reasons why there is a discussion about these large Himalayan earthquakes coming or not coming to the surface. And well, parts of the Himalayan front look like that. And yes, if I tell you here there is a fourth scarp crossing, okay, you have to believe me. But yeah, I mean, in Assam, you know, it's a region where it's raining a lot. There is a jungle, there is big forest, and certainly in 1950 or even earlier, when an earthquake occurred at the front of the range, well, it may stay unnoticed for obvious reasons. Still today, a large part of Assam look like that, and looking for evidence of surface break is not simple. Another aspect is that Assam, yes, it's the Far East India. Now things are changing. I mean, there are roads. Sometimes the roads are difficult. Certainly, there is a lot of water, and a lot of bridges are missing, and sometimes you have to carry your car on some of these small boats to cross the rivers. So, I mean, access is not so easy, but I think things become much more easier now. And what we did, in fact, in this project is to look at the mountain front around the plain here of Assam. This is Arunachal Pradesh here to the northwest. And we looked systematically at the foothills along the Abor Hills here, which is underlined by the main frontal thrust, and here along the Mishmi Hills, which see the Mishmi thrust coming out. And I will show you some of the sites located here in the region of Wakro, near Loitpur, Roing, and Passigat. So this is the first outcrop I want to show. This is so along the Mishmi Hill mountain front. What you see here is a river cut across an outcrop here. This is myself here for scale, and yeah, trees are very big in Assam. So what you see here is mostly this gray east-dipping conglomerate covered by a very young brownish conglomerate, which you can see are also over-trusted here in this part. I will zoom in this part now, and so you can see a little bit better. Again, this is myself here for scale, and you can clearly see these gray conglomerate over-trusted here over a younger conglomerate, which are more horizontal. Okay, so if I put some interpretations here, what you can see here also is this Mishmi thrust that outcrops at the front of the mountain with a dip of about 20 degrees to the northeast. So there is evidence that there is an active thrust here coming out at the range front. Now, if we look at terraces deposited by some of these rivers, you can see that they are quite flat, but they are sometimes cut and offset clearly by the emerging thrust fault, which is here, and builds up this high scarp, which is here. Oops, sorry, about 9 to 10 meters high. It's a quite steep scarp, and we think that this scarp is associated to the 1950 earthquake. At other places, again, you can see here a terrace, here the top, here the bottom part, cut by this scarp, which is, and you can see here some material of this very bouldery material of the terrace. The scarp is quite steep. We can do some topographic profile across this 15 meter high scarp. And what you get is something like that here. Again, the total displacement is probably about 15 meters, but the scarp shows some complexities, and with a steeper part here in the middle and some gentler part on both sides, which might be explained by, this complexity might be explained by the fact that this is a scarp that is built by multiple events, and here probably two events, similar-sized events of about 7 meters. When we go down along one of the river here, the Kamlang River near Wakro, what we see is here the present-day stream bed, and the first terrace here looks like that. You can see here a conglomeratic deposit on top of the bedrock here, and which is sharply here cut by the fault. We zoom here. Again, you can see here the stress deposit above the bedrock, and the offset of the surface here, if I put the interpretation, is about 7 meters. And we can also measure the offset between this bedrock limit between here and downstream, which is about 7 meters. So we think that this might be associated to the 1950 co-seismic offset. And as we go upstream here along the river, we can still see some rapids that might be associated also to the earthquake. This is naturally the scarp probably cut more in the front in 1950, but due to the activity and erosion of the river, this scarp is receding back upstream, and today we only see still a cascading river here, and this really looks, is reminiscent of observations that were done, for example, along the Kashmir 2005 earthquake, or even the Wenchuan 2008 earthquake in Sichuan. So just to summarize some of observation in the region of Wakro, so we could map a very continuous scarp that is crossing upper terraces, lower terraces, and we have, I think, a 7-meter offset, which is well identified on the younger terrace, and we have evidence at 2 places of cumulative scarp of about 14 meters, probably the result of 2 times, in fact, 7-meter earthquake, suggesting that the 1950 earthquake slip was vertically here of about 7 meters, and that the previous earthquake probably slipped with the same amount of displacement. Now we move towards Pasigat. Now we are looking at the frontier of the at the MFT, in fact, and this is a high resolution. It's a high resolution DEM from Pleiad images, and you can clearly see here the scarp in the topography. And if we look at different sections across the scarp, this is how the smallest scarp is evidenced in the city of Pasigat. The road is built on top of here of the scarp, which is about 2.6 meters high. And as we move to the south towards higher terraces, in fact, we can again see a scarp which is smoother and gentler than what we see along the Mishmi Trust, with amounts of 7 to 12 meters in height. And the idea here is that these terraces that become higher as we move here to the southwest have accumulated several, displacement that result from the accumulation of several earthquakes, the 2.6 meter being the one associated to the 1950 earthquake. So this is also a region that had been, which is characterized by many landslide scars that can be really seen in the landscape and can be also seen and mapped with satellite images. Some of these landslide scars are still active. And also some debris flow can still be seen in the foothills, and these debris flow are clearly characterized with these and loaded with these trunks, which resulted from the evacuation and the debris flow coming from upside in the forested areas into the Assam plain. And some of the first deposit along the rivers really looked like that, with many trunk debris that are associated to the debris flow triggered probably by the 1950 earthquake. At places, what we see are forest remnants. As you can see here, you see this 2-meter high trunk, which are completely beheaded and which were covered by a debris flow which is now eroding, and so now we see again these trees coming out from the debris flow, and we still see these pebbles sitting on top of these trunks here. So we can map all these features. What you see here so is this continuous scarp that we can observe at different points along the Abor Hills and the Mishmi Hills, and that we can then map from high-resolution satellite images. We map here as these circles all the evidence of landslides along the MFT and along the Mishmi Trust, and you can see that some of them can be followed very far to the south here, south of Vijayanagar. And we also map here in this light yellow all the evidence of debris flow that were deposited at the front of these two trusts here that were activated during the 1950 earthquake. So to put the things together, we think we have evidence of continuous scarp here along the two trusts, the MFT and the MT, with a probable length of 200 kilometers at least. And if we extend it to the southernmost evidence of landslide, it reached about 330 kilometers. These are some of the isosceles that were drawn following the 1950 earthquake. These are the epicenter of this earthquake, which is located here. So these are locations from different studies here from the 60s and 70s. We worked, mostly Emile, in fact, did work on this data. And so relocation of this main shock, in fact, I mean, is very similar to previous work. These are some of the focal mechanisms that were computed in the 70s for this earthquake. Very different focal mechanism. Here a strike slip one, and here a more thrust one. And this is the one computed after we mapped this scarp, and in fact, it's a focal mechanism that takes into account here the geometry of the fault derived from the mapping of this scarp, and which is in agreement also. I mean, which is in agreement naturally with the first motion arrivals that are also used in this focal mechanism. So these are the aftershocks that were also relocated during this work, which are widely distributed, but as you can see, there are a lot here north of the MFT and also here on the eastern part of the Mishmi Trust, which really suggests that this earthquake really broke the two faults together. Okay, I just put here again the mapping of the landslides that are here along the two trusts. Okay, and here I have another figure where we have, I mean, it's the model we can imagine for the two trusts, where a shallower trust associated with the MFT here with less vertical displacement, and a steeper trust associated to the Mishmi trust with larger vertical displacement that were activated together during the 1950 earthquake. So to go a little bit further with the field observation, here again you can see the scarp here offsetting one terrace here. And so in order to get some timing on the possible age of the penultimate earthquake, we did some dating that was already presented before. We used cosmogenic barium-10 measurements in the quartz-rich rock to constrain the exposure age of these terraces. And so, okay, and so we used surface blocks. We dated both surface blocks and subsurface samples in what we call depth profiles. This is an example of a big metric block here. We sampled the top of it, and we get some rock chips here that we processed and analyzed and measured the barium-10 concentration. And we also did this in a depth profile here in one terrace. And here I put together all the data we got. So this are the distribution of the barium-10 concentration at the surface. This is the one we got at the subsurface, and we can model this exponential decrease here of the barium-10 with depth, which is in agreement with the surface age we have here, which allow to constrain the upper terraces, which are offset about 14 meters around 2,000 years. And the younger terrace, which is only offset 7 meters, some of the sample here gave something very young, which is in agreement with its abandonment just after the 1950 earthquake. So these results so are consistent with the last event occurring in 1950 and with the penultimate event, which would be between 1200 and 2600 years. So I'd like to conclude with this. I think we have evidence of recent surface faulting associated to the 1950 Assam earthquake along both the Abor and Mishmi Hills front. Our field observation, both the continuous scarp over possible length of 330 kilometers, the geometry of the scarp, the geometry of the fault when we can see it in section, the amount of the offsets, the landslide extension, all agree with the magnitude and the magnet and the mechanism. The vertical co-seismic offset and dip of the Mishmi thrust and main frontal thrust imply up to 15 to 30 meters of slip during the 1950 earthquake, and which is in agreement with the magnitude 8.6 moment magnitude that is also derived from long period surface waves. And the resultant mechanism that combines the scarp observation along both the MFT and the MT is also compatible with the first motion polarities. So given present-day geodetic conversion in Assam, which are about 17 millimeters per year, and the maximum amount of slip that we estimated from our measurements, we obtain a recurrence time of such large earthquake, which is about 1700 years, which is also in agreement with the dating that we did on the highest terrace. Thank you very much for your attention.